Hello, thank you everyone. So today is my pleasure to give the tutorial for the potential DTALite and NeXTA users. My name is Shusheng Zhou, and I have been developing dynamic traffic assignment for almost 10 years. So in this tutorial, I would like to introduce our software package as well as the traffic flow models. And we have designed a number of modules. Hopefully, we can go through these modules and then help you to understand the traffic flow foundation, traffic assignment foundation, and the basic users tutorial, the users cases, so that you can be familiar with the large-scale open source package in almost one day. So my contact information is here, and as I serve as a associate professor at Arizona State University. Before I move into ASU, I have been working as assistant professor and also associate professor at University of Utah. And this tutorial is prepared by a number of students, including Jeff Taylor, Tony Liu, and also Dantin Wu, and I would like to express my thanks to them so that you can also contact them if you have further information, further question. So in this mini workshop, the purpose is to educate the workshop attendees on dynamic traffic assignment tools through some hands-on exercise, and particularly using our open source DTALite software package. And also, after you're going through all the basic modeling steps, I hope I can help you to import the data and modify a very small sub-area network and further evaluate the simulation results using some very advanced visualization tools, visualization features in NeXTA package. So in this mini workshop, I would like to have 4 modules with you. Number 1, I will give an introduction to the DTALite and the NeXTA package and some background traffic flow information. Number 2, I would like to introduce the DTALite modeling principles, including some agent-based shortest path calculation and some basic steps using DTA. Number 3, I would like to go through some visualization features with you. And then number 4, I would like to just go into some work zone and some pricing applications. So this is module 1. So in this module 1, I would like to present the objective of this tutorial, and I will show you what we can do by using this open source package. And also I would like to just go through the software package with you very quickly. So before I move into the DTA package, I would like to introduce, we have the 3 layers of large scale, region scale, and also intersection level simulation, if you want to call that. So we have the macroscopic simulation, typically is a static traffic assignment. A mesoscopic simulation, we simulate the traffic agent by agent. And also we have this car following type micro level simulation. The typical package could be vSUM, could be Paramix. So if you ask me what are the major differences between the 3 layers of traffic simulation package, if you go to the very up level, typically the resolution, the temporal resolution is hour by hour. On this meso level, the temporal resolution is 6 seconds. As you know that 6 seconds per simulation interval, and then if you have 1 minute, you have about 10 simulation intervals. Then if you go to a car following type simulation, we need to model all the detailed lane changing behavior. By doing so, we need to keep a very high fidelity simulation framework with a simulation interval such as 0.1 seconds or 0.2 seconds to literally check all the movement of a car following behavior. And if you go to this regional level simulation, the purpose is to get a network-wide traffic performance. If you go to the meso level simulation, the purpose is to evaluate all the advanced agent-related features, such as they have different value of time, different rule choice property. And if you go to the conforming level simulation, you need to literally represent the traffic signal lights, represent the merge, diverge, all the detailed driving behavior in this particular scale. Okay. So I would like to present this system architecture of the DTALite with you. If you can see the screen on my other side. So typically, I would like to start with, in the middle, we have the DTALite Mesoscopic engine. This is a traffic assignment engine. So we have, number one, we read the node and the link network data into the DTALite. Number two, we need to define the OD demand matrix, origin destination demand matrix. And we can consider time dependent, hour by hour, or 15 by 15 minute demand matrix into our simulation engine. Number three, we can model a set of scenarios such as traffic work zone, traffic pricing, signal optimization, and ramp metering, a number of those traffic-related scenarios into our simulation engine. So if you try to consider some emission applications, you need to consider vehicle type, you need to consider the age distribution for different operating mode. So after that, from the middle of our simulation engine, DTALite, you can produce the vehicle trajectory. If you want to do a emission-related analysis, you can do a second-by-second vehicle speed based on newest car following model. You can also produce the vehicle emission data and then also produce other network-wide traffic statistics. I will go to many layers of statistics analysis in the next few sessions. So since typically we deal with a large-scale network, by large-scale network, we can talk about the city of Phoenix, city of Beijing, and typically they have 1 million or 10 million population, and typically one person might correspond to 3 trips. And then during 24 hours of a day, we need to simulate all those individual travelers throughout the network. The network size typically is 50,000 nodes or 100,000 nodes and 2,000 links. I will say 20,000 links. And by doing so, we need to deal with a number of computational challenges, such as shortest path calculation challenge, the traffic simulation computational challenge. To attack those challenges, we enable a parallel computing facility, OpenMP. So we will do as we can show, we can see from the presentation, we will do the agent-based routing from zone 1, zone 2, zone 3, different zones across different CPUs. And also we have a very efficient traffic simulation using this parallel computing structure. So before I move into any detailed traffic flow simulation package, I would like to take about 10 minutes or 20 minutes to introduce the traffic theoretical foundation, LWR equations. So typically, the traffic flow can be viewed as a traffic flow stream governed by a number of important equations, such as this flow balance constraint. We have this set of the partial differential equation. And we also need to have the traffic speed flow density relationship, such as the Green-Shores model. And before we go into more details, I'm assuming that you have enough or sufficient background about the traffic stream, such as flow, Q, density, K, and V as the speed. Okay, so this is a set of 3 major components of LWR equations. hyperbolic system of conservation laws. So many users might ask me, what are the traffic flow model we use in DTALite? And I need to present a very typical cell transmission model, CTM, in this particular process. So in a numerical calculation scheme typically used in a discretized network, we have delta t, the length of simulation interval, as 1 second or 6 seconds. We have a link or cell being used to represent the spatial characteristics of the network. So if you want to do a cell transmission model, you might need to model the cell with a length of 0.1 miles or 0.5 miles. And then in our representation, we use the link directly from the physical representation from our planning model. Then we need to calculate the density K at each link, and we need to calculate the speed at each link at each 10t. Then further on, we need to calculate the flow, being the transfer flow rate from one section to the other section. So typically, we have 3 or 4 steps to really move the vehicles. Number 1, we need to calculate the prevailing speed, calculate the flow ready to move from one cell to the next cell, and then calculate the corresponding transfer flow by considering the demand and the supply function. Then finally, one need to update the prevailing density. So I would like to really show you that in the typical cell transmission model or a flow-based representation, the representation component here is flow, is a fluid. They are not the agents. So by saying so, I would like to just make sure you can understand the difference between the agents as the particles or the flow representation and the fluid. Using fluid representation is computationally very efficient, but it has difficulty to represent the agent-specific information such as origin, destination, routes, and also different value of time related to the income level, so that you can really simulate those individual particles throughout the network. Okay. So what have been used in the open source dynamic traffic assignment DTALite is newest in-curve or cumulative flow count approach. So by using these cumulative flow counts at location I at 10t, we can literally derive the flow rate and the density. Okay, so basically is we simulate a number of agents throughout this intersection, and we can always count the incoming flow cumulatively, the outgoing flow cumulatively, and then we can draw the corresponding cumulative arrival, departure curve, and then calculate the corresponding flow rate and the density as a number of vehicles or number of agents in the system. And then if we try to calculate how many vehicles being transferred between those transfer points, then we can use those in-curve propagation to do the calculation. But deep inside, when I try to implement this simulation model, I don't literally just only use cumulative flow counts. I still need to move the agents, agent by agent, to see how the capacity being distributed. So if you want to look at the Q spillback or the shock wave or some complicated traffic flow shock wave features, we use the backward wave propagation as a session. So you can refer to the white paper of the DTALite to know more details about the backward wave propagation using Newell's model. Here I do not go into more details. So if you look at this particular graph, I would like to use this illustration to show I have 2 sections. This is section 1, section 2. I have 3 nodes, I minus 1, node I in the middle, node I plus 1, and then I have 2 types of waves. Okay, this is in this time and the space diagram. We can try to send the vehicles along the green wave. This green wave is the speed limit. Okay, speed limit. And then if you have any congestion from the downstream segment or from the downstream node, at the node I plus 1, then you can see a set of backward waves. Those are the result of car falling. Those are the result of the car falling. And then those backward waves will be propagated throughout this wave, throughout this space dimension, and then finally along this dashed line, I would like to say 1 minute before you have a congestion, and then throughout this backward wave line, and then this congestion will be propagated to node I at this particular time stamp t, so that this whole intersection or this whole section will be congested. Okay. Along this wave line, the density is the kgm. This density along this waveline is a kgm, so which represented by this particular equation. So summary of this traffic flow comparison is that in a typical set transmission model, the CTM might use density, incoming flow, outgoing flow, and the speed as a fluid-based representation. But using the newest model plus the agent-based representation in the DTALite, we can model the incoming, outgoing, cumulative flow counts, and then from here we can derive the density, float, then to get other statistics. Here is one very important remark. We do not, in the DTALite, we do not have the direct speed measurement or the speed representation for each agent because we use the newest link transmission model. So we can literally check the incoming timestamp and the outgoing timestamp along a link, and then from the link travel time, we can back calculate the speed. So we do not maintain the speed measurement every second. We back calculate the speed from the link travel time measured. Okay, so in this representation, we also try to simulate the traffic flow as a simple queue. So in this queue-based representation, we have the inflow queue here, we have an outflow queue here. So typically, a vehicle will be sent to this inflow queue and then sent to the outflow queue using the free flow travel time first. If that available capacity at each simulation interval, and then this vehicle will be sent out further. So using this queue-based representation, we ignored, by saying so here is, I ignore all the details in the lane changing and also the car flowing inside the segment or a link. But by doing so, I can very efficiently calculate the flow propagation and also the travel time, and then represent the work zone propagation, incident propagation to the network level. We have a few more animation later on to show the complexity of a link and a path-based model. So here, when we have a merge or a diverge intersection, we need to pay some special attention. As we can show here, this is a link ij. We have two merge links. So this is a very idealized representation. You can try to view in practice. This is a freeway. This is the merge or on-ramp. This is another freeway section. This is off-ramp section. So when you have two links competing the limited capacity in the middle, then we need to enable this realistic representation of capacity distribution. For example, I have one vehicle, another vehicle, two vehicles competing for 1 unit of the capacity available at this time simulation time interval. We need to first of all decide the proportion of capacity split for those two incoming sections, and then when we try to simulate the agent when we try to simulate the agent moving, we need to flip the coins to run a random number generator to generate those random numbers, so that I can decide at a given rate how an agent moving from one link to another link. So similarly, when you have this diverge intersection or diverge freeway section, you need to simulate the Q spillback along the freeway. So before I move into more details or the more practical consideration, I would like to use this simple illustration to show how literally the DTALite has to keep track of the capacity allocation. So in this x-axis, this is a freeway on-ramp. On this y-axis, this is the freeway mainstream section. This is a mainstream section. So suppose on-ramp have one lane. This mainstream section has 3 lanes. So the capacity, so the demand available on D1 is about, say, 3,000 vehicles. On the on-ramp, the demand to be released into this bottleneck is 1,000 vehicles. Then you have 3,000 plus 1,000. Then in total, you need to require 4,000 vehicles as a capacity. But unfortunately, if there's only, say, 3,000, or maybe 2,000 capacities available at the downstream, then you need to decide what's the proportion for you to split the capacity between the on-ramp and the mainland stream. So there are many different rules for those. Capacity distribution ratio, and in the DTALite, to be realistic or to be stable, we use the number of lanes. We use the number of lanes to split the capacity computation. But in many realistic cases, the mainland stream might block the on-ramp entrance, and also some aggressive on-ramp vehicles might block the mainland stream traffic. So for this merging model, if you want to have a very realistic representation for a freeway segment, you need to do a lot of detailed calibration. For a network-wide application, since there's so many different merge, diverge, all the different complex cases, and we need to enable a fast simulation, you might need to use our default model as is, and in the future, literally to keep track of this representation and have a more data-driven representation and then move forward. So, as I mentioned here, the DTALite is a mesoscopic simulation. So we move the vehicles. Each vehicle carries its origin, destination, departure time, path, specific information instead of the continuous flow. So when I have a flow or have a one unit of agent moving to the different divergent or the next intersections. For the fluid-based model, such as a set transformation model, such as some higher order model, they might use turning ratio. They might use some spatial distribution artificially, just split the outflow, say 75% to mainland, 25% to the off-ramp. But for our agent-based representation in the DTALite, we can move those agents directly based on their path. So the number of agents moving downstream to the mainland and off-ramp are deterministic based on the agent-specific attributes. Okay. So another major component in the DTALite is the time-dependent shortest path algorithm. You are more than welcome to look at the open source code available in the GitHub website. So many students might know, due to the last almost 7 years, we developed this open source DTALite. We have been having this repository, sometimes in Google Codes, sometimes in SourceForge, and now we all merge everything in GitHub. Okay. So in the DTALite shortest path calculation is a time-dependent shortest path algorithm is mainly based on the label correcting implementation in DynaSmart. Okay, since I'm also a former developer for the DynaSmart, led by Professor Hani Mamasani, currently at Northwestern. So we have a C++ implementation. We use STL, the standard temporal library, for the complicated data structure, such as multidimensional vector list, some hash table. Those are the advanced C++ feature to capture for us to keep track of all those advanced attributes. So we also use the OpenMP, enable a multiprocessor simulation, and we use a label correcting algorithm with DQ double buffered, and we calculate the shortest path based on the origin or based on the single departure time. Okay, so after we finish this 1.0 session 0 in module 1, we almost going through these very little details in the traffic flow foundation. Now we need to begin talk about how the NeXTA and the DTALite package can do for you, maybe for a practitioner or maybe for a researcher interested in this emerging traffic flow simulation field. So what we can do in the DTALite, we can do a lot of data importing and exporting. For example, we can import the data from GIS package such as a shapefile, and also we can import the traffic flow and also traffic demand model from the static traffic planning package such as a vSUM, Transcat, or Cube. We can also make the connection with the signal optimization tool such as Synchro, import the data from the Synchro, save it as a standard traffic signal data format, and then do some mesoscopic traffic simulation along this line. Then for the large scale dynamic traffic assignment, so typically we have 2,000 or 4,000 zones. A zone represents a traffic analysis zone, and we simulate about 20,000 or 50,000 links. Then we deal with 2 to 4 million agents or vehicles. The largest application we have is from the University of Maryland, and we simulate the statewide traffic flow dynamics for the statewide model of Maryland. Then the number of agents or the number of vehicles in that region is about 10 million a day. We also can do some network scenario analysis by enable this rich output, and then we have a number of low pricing application to consider time dependent toll, to consider these different value of time of different agents. So this is the one representation we have for us to show that the NeXTA itself as a graphic user interface, we can import many different data sets. This particular application is conducted with a connection with Kittison Associates at Portland, United States. So on the left, you can see we import the synchro data into the data hub, and then on the right, those are the planning package, and then we merge them together. We use this standard traffic signal representation with the planning package. Typically do not have the signal representation, and then we can simulate the traffic agents representation inside the vehicle, and then we can further explore them into different mesoscopic simulation and then make some representation. So we also, in order to make a very realistic representation, in the DTALite, a very unique feature is we can do OD demand calibration using the sensor data. So what we do here is typically we import the GIS package from the TMC traffic message center directly into the NeXTA, and then we can match those sensor links with the underlying traffic flow or the underlying traffic link representation in the DTA, and then we can import the speed data, we run the OD estimation iteration by iteration. Finally, we can calibrate those OD demand matrix based on the available speed or flow or travel time counts. Okay. So through all these process, we hope we can help you to enable the DTALite, and then to make sure that you understand the DTALite basically is a capacitated dynamic traffic assignment, which means we mainly just consider all the capacity impact from the bottleneck to the downstream bottleneck, from the upstream bottleneck, and we try to enable a very mathematically rigorous and also computationally efficient tool to evaluate many pricing and many work zone applications. By doing so, we try to enable the practitioners to assess the corridor level, network-wide effects, and then they can do many alternative comparisons, and then to analyze the corresponding recurring or non-recurring congestion. So the history of the DTALite actually coming from almost 2008 or 2007. In 2009, there's a TRB Network Modeling Committee, and then almost 10 years ago, we want to use the dynamic traffic assignment by many community users or members in the United States. The TRB Network Modeling Committee in 2009 conducted the DTA user survey. Many users say, I want to use DTA, but there are three major technical barriers to prevent the use of the DTA. One is too many input data. You need all the detailed geometry representation, which is very difficult. It takes too long to run. 35% users has some similar complaint. And also, since the DTA itself is a very theoretically involving model, so how to open up the detailed representation is quite important. So our goal here is, first of all, we start with a simplified data input from the static traffic assignment. We enable the parallel computing to do a simplified routing and simulation. And also we want to use the open source visualization, open source traffic simulation to help you to understand the details of all the simulation model. And then we do have a number of Excel teaching tools to help you to start with the basics. On the 1.2, and I have a similar page here for the practitioner. So many practitioners, when they use the DTALite, they always ask me, can I try to import the data from Synchro? And then you can estimate the OD demand pattern. Then you produce the simulation input into vSim. My answer is yes, we can do this process, but you need a good understanding of the mesoscopic simulation. On the other hand, the vSim type simulation requires a very detailed traffic flow and also a very detailed lane-specific representation, which is not captured by the DTALite. I would like to say it's easy for you to make the data conversion, but it's more important, it's more time-consuming for you to understand all the connections. So I encourage you to go through this process and then try to use your judgment to use the mesoscopic traffic simulation in the middle to get the best representation in your project. So we have a number of network scenario analysis. So as we go through this process, I always hope all the students, all the users can use the DTALite or use the NeXTA to make the scenario by scenario comparison. It's not about just making the simulation and the one run. It's about you have one scenario maybe with a high demand, one scenario with a low demand, and then when you make the two simulation runs, you can try to compare all the statistics into the in the NeXTA comparison, such as for the whole network, average travel time, for the whole corridor, for a typical link, for a selected link, and then by making those comparisons, it will enable you to think through the whole analysis process. So one typical simulation in NeXTA or in the DTALite is many years ago we have been working with the NC State, North Carolina State University, for their regional-wide network. And the number of zones is about 2,000, 9,000 nodes, 20,000 links, a number of signals. And at that time, the simulation time is 2 minutes, 45 seconds per iteration, and then 20 iterations per hour. It's almost 5 or 6 years ago. In the DTALite, one component I would like to highlight here is the memory consumption could be a little bit enormous, but given the emerging technology, typically we have 16 gigabytes of memory, and if you want to run a region-wide model, you might need more memory space to support the agent representation. Each agent has all the different paths. So we will spend some time today to look at the rich output of the NeXTA, and we can have other visualization form in NeXTA and in Google Earth, in other 3D animation. But more important thing here is you need to understand in the NeXTA interface itself, it has a wide range of vehicle, origin, destination, all the temporal spatial component for you to use it. Okay, and what I hope by developing this NeXTA as a data hub, we need to enable this data hub concept. We have been seeing many applications just try to connect the data component A to B, A to C, and then in this NeXTA data hub, we try to have the sensor data, traffic demand data, some traffic signal representation, some emission modeling details, and some activity-based representation for the region-wide in a planning model. So we try our best, try to make it open, try to make it more systematic for the users to understand all the connections we can make. So my goal for developing the open source NeXTA interface is that it will enable you to have a good understanding of how the different data sources can be mapped into one place, and then to do the traffic flow simulation into many different application domains. Section 1.3. So we have been talking about the traffic flow dynamics, the application. Now I need to go through this open source free software package. By free, what I mean is you can download the software package from the GitHub, but on the other hand, you need to learn. You need to spend some time to learn the DTALite or open source package, and then we are more than happy to help you, but you might need to spend some time to going through the details. So we have different versions throughout these years. NeXTA is a front-end graphic user interface. So as you can see here, this is our NeXTA interface. We have different versions, and thanks to the support of Federal Highway Administration, we have been developing this open source package as a visualization tool for DynaSmart transits, for DTALite, and also we are able to import the different data sources, including Google Transit feed, traffic volume, speed, GPS data, and then we hope we can do more connected representation along this way. The DTALite package is also a C++ engine. The number of lines for the DTALite is about 50,000 lines, and then the NeXTA as a very complicated visualization interface has about 200,000 lines of the C++ code. So in this page, I would like to show you can download the software package in the GitHub, and there are a number of training material or the learning document also in the GitHub. If I want to download the source code of the DTALite, you can go to this package to download all the required source code and a development environment along this way. So for a standard NeXTA or DTALite package, here is folder structure. Okay, so you may see two executable here: NeXTA.exe, DTALite.exe. So those two executables represent the front-end GUI and the computation engine. And then for the users, you just need to click on this NeXTA.exe. And by default, we are assuming that now you are using a 64-bit operating system. Okay. In this installation folder, you have the documentation, you have the required software package, and you have some toy network example. And then more importantly, you have a set of learning documents from 1 to 9, and have a set of corresponding data set from 1 to 9. By doing so, we already enable a learning environment or an open learning environment for you to understand how the traffic simulation can be performed, and how you can understand those user's guide and the system design throughout this process. Thank you.